Alright everybody, welcome back. In this video we're going to talk about concepts from section 8.6 of AP Calculus, finding the area between curves that intersect at more than 2 points. So up to this point we've largely looked at regions where there was just one region that we were finding the area of. But in these situations today we're going to look at graphs where we have multiple regions and how we're going to deal with that. There are going to be two good ways for us to deal with this. We're going to look at one of those ways in our first example, and then we'll look at the other way in the second example. And, you can kind of use them depending on the situation that you're in. Determine which of those methods is best for you. Okay, so our first method that we're going to do is we're going to be subdividing the region using the intersection points of the curves. In order to do this, we're going to find all the intersection points of the curves in question. And then we're going to write integrals for each region. And when we do that, when we write integrals for each region, we need to make sure of two things. We need to make sure that we're using the appropriate coordinates for the limits of integration for each of our integrals. And we also need to make sure that we're using the appropriate curves as the upper and lower curve, that we're paying attention to which curve forms the upper boundary of the region and which curve forms the lower boundary. All right, example 1. Find the area bounded by the curves y equals 1/6 x cubed minus 1/3 x squared minus 11/6 x plus 2, and y equals -1/2 x plus 2. Okay, so if you look at these, this blue line here, that's the y equals -1/2 x plus 2, and this is the cubic curve in red. Okay, so as I look at these two curves cordon off two regions. This region right here, and this region right here. And so when we're finding the region here, or the area, we need to find the area of each of these two regions. Alright, so I'm going to erase that shading so that we can see a little bit more clearly. And what I have here is I have three intersection points for these curves. I have this point right here, which is the point -2, 3. I have this point right here, which is the point 0, 2. And I have this point right here, which is the point 4, 0. Now, easiest to do this as functions in terms of x or in terms of y? Well, considerably easier in terms of x, since it would be very, very difficult to solve this and get it as x equals a function of y. So we're looking at, vertical strips for each of these regions as we're calculating the upper curve minus lower curve to build our integral. So our first integral, it's going to be the integral from the left end to the right end of this first region. So the integral from -2 to 0. And on this interval, the upper curve is the cubic function. So I'm going to write that function first. We're going to have upper curve minus the lower curve on that interval, which is the line. And that integral is going to give us the area of this first region. And then I need to add to that the area of the second region, which is going to be the integral of. And for that region, the line forms the upper boundary. And so the line is going to come first in our integrand. And we're going to have line minus cubic function. And we're going to integrate from one end to the other. And that starts at x equals 0 and ends at x equals 4, so those are going to be my limits of integration. Alright, now, given the curves that I have here, I could totally go ahead and integrate this by hand and find the antiderivatives, but for the sake of time here, I know that I know how to find those integrals. For the sake of time in our lesson here, we're just going to go ahead and integrate this using our graphing calculator. And so we've got the integral of 1/6 x cubed minus 1/3 x squared minus 11/6 x plus 2 minus the quantity negative 1/2 x plus 2 with respect to x from negative 2 to 0. That's the first integral, plus the integral of negative 1/2 x plus 2. And of course, if you're using a TI-83 or 84 series calculator or some other calculator, whatever your syntax is for taking the numerical integral is what you're going to want to use here. I sometimes forget I'm not using a calculator that's super used by people, but it's the calculator that I tend to have. Same calculator as my personal calculator. And now I can go ahead and hit enter, and uh-oh, I'm missing a parenthesis. Is it here? All right, let me double check and make sure I typed everything in correctly. It looks like I did. And so the value for this area is going to be 8.222, or 8.2 repeating, or whatever that is as a fraction. Let's see, that's 8 2/9, so that would be 74/9. So those are all acceptable final answers here. All right, so that's one method. We can split it up into multiple integrals. All right, second method is going to be to utilize the absolute value of the integrand instead of splitting it up. Some advantages that we have to this: we don't need to worry about the intersection points. Okay, we only need the endpoints of the entirety of where the curves overlap. We don't need to worry about putting the correct curves in order as the upper and lower curves in our integrands. It doesn't matter what order we put them in when we use the absolute value method. Big disadvantage to this is that taking the integral of an absolute value is difficult. And so I highly advise you to only do it, when you've got a calculator in your hand. I mean, we can do it by hand, but it gets a little complicated, and it's not significantly easier to do by hand than just splitting the region into multiple integrals. So keep that in mind. All right, so we're looking at example 2 here. We're going to find the area of the regions bounded by these curves, and we're going to do it using the absolute value. So for my integrand, it doesn't matter which order I put these in. So I'm going to take the integral of the absolute value of, and I'm just going to take the first listed curve, the sine curve, minus the second listed curve. Okay, now on this interval, the sine curve is bigger than the line, and so the absolute value of it is just exactly the sine curve minus, it's exactly what's inside here. On this interval, this is what's inside the absolute value is the opposite of what's inside of what I would write if I wrote this normally. Normally I would write the line minus the sine curve to calculate this area, but taking the absolute value of that gives me the same numerical value no matter what the order of our two lines are when we write them. And so now all I need is my limits of integration, and I'm going to have to use my calculator here to find those. This is a calculator active problem. 2 sine of pi over 3 x and y equals 1/2 x minus 1. We'll look at the graph here. I'm going to have to change my window a little bit, extend it over there, the X max. Extend that out. Since I didn't quite get the graph on there. There we go. Okay, so now I just need the intersection points at the endpoints. So first curve, second curve, my lower bound is way over here. So the x-coordinate here is going to be my lower limit of integration, negative 1.801839. And my upper limit of integration is going to be this endpoint all the way over here on the end. And we get 2.8062052. 2.8062052 as our intersection point there. All right, and now we have everything we need to find the area of these two regions. I'm going to go out to my main screen, and we'll take our integral of the absolute value. Hopefully you know where to find the absolute value command on your calculator. 2 sine of pi over 3x. I know if I'm using a calculator that I'm not used to, I typically look for the catalog of all commands and let it search for that. Close my absolute value. We'll see how my calculator does with this. Now, one thing, especially when we start to use absolute values in integrals, is sometimes it takes our calculator a little while to go through the algorithm and calculate the values of these integrals. For instance, my calculator has already been running on this integral for almost 15 seconds, and there's no progress in sight. Oh no, my calculator does not like this integral. Oh no. So this one, if I were doing this on my calculator, I would have to split it into two integrals because my calculator won't calculate the absolute value. I'm going to use my other calculator here, if I can get it to turn on. And there we go. We're going to do the numerical integral of the absolute value of 2 sine of pi over 3x minus 1/2 x minus 1. Close that up, close the absolute value with respect to x from negative 1.801839 to 2.806252. And I'll hit enter and let that thing calculate, and hopefully it'll calculate it before I run out of time. We're running low on time. So hopefully it'll spit this number out in time for me to jot it down before we sign off. But join us next time. Hey, there we go, 5.172. Join us next time when we get into section 8.7 of AP Calculus, where we're going to start finding volumes using integrals. All right, see you next time, everybody. Have a good one. Bye-bye.